All right, let's take a look at this one. So we have three charges, one, two, three, and all the charges are given here, right? So as always, try to identify important information from the questions, and then it helps if you just label the charge on the diagram like this, and then the distance is given like here at 5 millimeters. So A is 5 millimeters. So that means 1 and 2, these two guys are, you know, a distance of, square root of 2A, right, apart from each other. So that's a simple Pythagoras theorem. So what do we need to find? Well, we need to find the magnitude and direction of the electric field at point P due to the three charges, right? So this is where you need to add the electric field from each charges in a, you know, like when you add vectors, right? So that's probably the most important thing for this problem is you realize that electric fields are vector. Okay, so I'm gonna redraw the diagram here so that it's a bit easier to deal with. So we have plus E here, and we have plus 2E, and then we have plus E here, and then we want to find the electric field at this point. Okay, so if we look at these two, right, they are along the same line, which is good because plus E here and plus E here are equal distance away from this point, right? So the electric field from charge number 1, which is this guy, will point this way, right? Because it's positive charge, so it's point away from the charge. So electric field from 1 is this one. Electric field from this one, which is the second one, is pointing this way. And since they are equal distance from each other, they probably just cancel out, right? So this one and this one gonna cancel out. So the only thing left that you need to figure out is the electric field from this guy here. And that's gonna be pointing that way. Okay, so that's the answer for A. So for A, the electric field is equal to K Q3 divided by R squared. And Q3 is 2E, so it's 2 times 1.6 times 10 to the minus 19 coulomb, right? So I'm not gonna spend too much time, cranking number that you can do by yourself, because we have quite a few problems to go through. All right, so that's gonna be the magnitude. We also need to say what's the direction. Well, due to the geometry of the problem, it's gonna be 45 degrees, right, from the horizontal, like this, right? So you can say the electric field magnitude is given by this number, and the direction is this. Okay, or you can do it like the I and J kind of, component. Like you can say the electric field is some number I plus some number J. That also works. Okay, and the other thing that you need to be careful is this R here. That's the distance from charge Q3, charge number 3, to that point P, right? So it's gonna be root 2A divided by 2. Okay, so it's this distance here. Okay, this is R. Okay, so I hope this is not too difficult, right? Again, you probably need to put in the number yourself. So let's go to the next one, which is B. So for B, we say that if we have the fourth charge and it's put here at point P, what is the magnitude and the net force on Q4? This is where you use F equal to Q, well in this case Q4 times electric field at point P, right? So you already have electric field given, calculated in, you know, question A. Then you just multiply by Q4. And the only thing that you might forgot is that it's a minus sign. Okay, so it's a minus sign times the electric field. Okay, so the magnitude you can just do the number, but because of the minus sign, the direction of the force will be opposite of the direction of the electric field here. So the direction will be pointing this way, 45 degrees. Okay, so the direction is opposite from electric field because Q4 is negative. So this problem is a nice demonstration of why we use electric field most of the time, right? Because if you change Q4 from this value to other value, you don't need to recalculate everything, right? Because no matter what charge you put, you just put it here. The electric field is going to be the same. All right, so once you figure out the number, then that's going to be the answer for this question. Okay. All right, so any questions so far? Well, if not, then let's move to the next one. And again, I'll give you a few minutes to think about this. Okay, so let's take a look at this. This is a problem where you need to understand the relation between, potential energy and um, how it's related to kinetic energy. So you have two plates, one at 100 and the other one at 500. And you can safely say that in the middle is probably something like this, like half, 250 volt. Okay. Um, so that means we have here a proton. A proton is fired with speed of 200,000 meter per second from the midpoint of the capacitor towards the positive plate. And you know why it's gonna turn around, right? Because it's positive charge. It's gonna get repelled by the positive plate here, right? So if you don't fire it fast enough, then it's not gonna reach the plate here. Okay, so show that this is insufficient speed to reach the positive plate. Um, it's probably maybe easier if you just calculate what's the required speed to shoot from here to reach the right plate. Okay, and it's a proton, so we know the charge, right? So we have the mass of the proton. Uh, Sorry, can you? I have a drop connection for a second. Can you all hear me now? Yes. Okay. Good. Thank you. So it's a proton, so we know the mass of the proton. We're gonna be needing it about 1.6 times 10 to the minus 27 kilogram, and the charge is positive charge, right? So let me write Q is about also 1.6 times 10 to the minus 19 coulomb. So from here, in order for the charge to reach the right plate, it must have enough kinetic energy to reach the plate, right? And going from the middle to the right, you increase potential energy, right? Because what's the potential energy? Potential energy is the charge times potential, but charge is positive, right? So if the potential is positive, potential energy is positive. Okay, so this is similar to throwing a ball upwards, right? When the ball is going up, you decrease kinetic energy while increase potential energy. So it's kind of the same thing here, right? So let's calculate how much speed you need in order to reach the 500 volt side. So you can just say, okay, let's say this is 1/2 mv square, and in the end it's gonna stop here. Let's say it stop just before 500 volt. So at this point, there's no kinetic energy, so V equal to 0. Right, so kinetic energy becomes potential energy. But how much potential energy you gain? Well, that's going to be the difference between the potential here and here times the charge, right? So the change in the potential is charge times the change in the change in the potential energy, delta U, is the charge times the change in the potential. So that's going to be Q times 500 volt minus 250 volt. And that's going to be 1.6 times 10 to the minus 19 coulomb times 250 volt. Okay, and that's going to be in joules. And this is how much energy you gain. So you got this from 1/2 mv square. Right. So you equate this to be 1/2 mv square equal to 1.6 times 10 to the minus 19 times 250 volt. And then you can calculate the velocity. So in this case, I will calculate it because it's probably easier if we have the number. Okay, so v square is 5 times 10 to the 10, I think. So v is about 2.23 times 10 to the 5 meter per second. Okay, so this is what you need to be able to reach the positive plate. And you can see that this is larger than the number given here in the problem, which is only 2 times 10 to the 5. Right, so you don't have enough kinetic energy to reach the positive plate. So that takes care of the first problem. Show that this is insufficient, so we already showed that. The other way to do is to calculate like where does the particle turn around. That's gonna be a little bit more complicated because you need to maybe put in the number about like the separation between the plate or something like that. But it's also doable. So it's a little bit more complicated. So I suggest that you do it the way that I just did. Okay. So what else? The second one, what is the proton speed when it's collide with the negative plate? So the way I would do is this. So we know that the proton will go to the right and then turn around and then go to the negative plate, right? But because of the conservation of energy, by the time the proton are turned around and then back to the middle point, right? The proton will have the velocity going to the left. But since it's back to the same potential, the kinetic energy has to be the same because you didn't gain any potential energy in this case, right? So again, it's very similar to the free fall problem where you throw the stone up and then down. So right when it passes through your hand, the velocity vector flip, right? So you have the same kinetic energy, but it's just different direction for the velocity, right? So the problem simplified to something like this. So I have the negative and positive plate here. So this is negative plate, this is positive plate. So the question is becoming something like this. So if I release the proton here for 200,000 meters per second in the middle, what's the velocity of the proton when it reaches the negative plate, right? So again, we can use the conservation of energy, right? I can say this is 0.1, this is 0.2. So E1, which is the total energy at 0.1, it's gonna be 1/2 mv square, V1 square, plus the potential energy at the middle, which is 250 Q. 250 is the voltage, is the potential, right? I shouldn't write it this way. I just maybe write big V times Q like this. Okay, so that's the potential at the middle, which I call V1. And then at 0.2, the potential is 0, so I don't need to write the potential energy. But the kinetic energy is going to be more, so it's going to be 1/2 mv square, where V here is V2. This is V1. And because of the conservation of energy, then they are the same, right? So I just say 1/2 mv1 square plus V1. This is different V, right? One is velocity, the other one is the potential, equal to 1/2 mv2 square, like this. Okay, so solving this, we have V2 square is 2 big V1 Q divided by M, and then plus V1 square. So putting this number, then we have 2 times 250. That's the middle point, right? That's the potential for the middle point, times the charge, which is 1.6 times 10 to the minus 19, divided by m, 1.6 times 10 to the minus 27, plus v1 square. v1 is 2 times 10 to the 5 square. Okay, and then this one, well, I'll just leave you to do the number cranking because it's just plugging into the calculator. All right, and then don't forget to take the square root of this whole thing. Okay, but this is how you do it. So before we move to the next question, the thing is that you can ask yourself, what happens if I replace proton by an electron, right? So things gonna be different. If you put electron here in the middle, the charge is negative, so the potential energy will be negative because you need to multiply by negative charge, right? So for electron, it will have no problem reaching this side because it's attracted to that side anyway, right? So that's going to be a different case. So that's a very important thing that some of you miss during the exam is, well, not some of you, like some of the previous students miss during the exam, is that you know the potential, but you need to multiply by the charge to get the potential energy, and depending on the polarity of the charge, whether it's positive or negative, right? Sometimes you get positive potential energy, sometimes you get negative potential energy, right? So that's gonna be quite important when you do this kind of problem. All right. Okay, let's move to the next question, which is this one. So this one might look a little bit scary, but it's actually not. So again, I'll give you a few minutes to look at this and then see what you come up with in terms of the solutions. Okay, so this one again, it looks a little bit scary because it might seems like you need to do a lot of integration or something like that. It's actually not, um, and that's because we are talking about here about the potential. If this problem asks about electric field, that's totally different thing. But this is potential. Potential is scalar, so you don't need to worry about the direction or anything. Okay, and if you look at every element, so let me zoom in a little bit. If you look at every element on this curve, no matter which point you pick, it's gonna be the same distance to the center. And remember, the potential V is given by K Q, whatever Q is, divided by R, right? So if you have multiple charges, right, remember, so let's look at a simpler case. Let's say you have Q1 here and then Q2 here. And then you're interested in this point here, right? And even better if we set those two to be the same distance from this point. So what's the potential? Again, if we are talking about electric field, you need to draw a vector and then you need to add a vector like this. It's quite complicated. But for potential, again, it's a scalar. So we just do V1 plus V2. So V total equal to V1 plus V2. So it's going to be KQ1 divided by R plus KQ2 divided by R. And that's it. Okay. And then you can imagine adding more points, more charge, like this, right? So just in the end, adding up every charges in this way. So if you go back to this diagram, right, for Q1, the total charge is 5 NC. NC is nanocoulomb, right? It's 10 to the minus 9 coulombs, right? So if you divide the charge into different chunks, so each of them you just need to do KQ divided by R, but then when you add up all together, you just recover the total charge again, right? So that means what you need to do is just adding, well, not, you don't even need to do that. You just say, okay, it's the total charge Q1, which is the distance R away from the center. So if I write V1, it's gonna be K times Q1, which is 5 nanocoulomb, divided by R. That's it for the Q1. For Q2, it's the same thing, right? Q2 is minus 2 of Q1, so it's gonna be minus 10 nanocoulomb. But again, it's distributed along this curve, which is equal distance from this point here. So you can just add up, and then when you add them up, you're gonna have the total charge to be, minus 10 nanocoulomb. So V2 will again be K times Q2 divided by R. And this problem is very simple because the fact that every point on the curve is the same distance to the center. If you are talking about different shape, then it's gonna be a little bit harder to do, right? Maybe if you have like the shape that looks like this, then this point will be closer to the center. So 1 over R here will not be a constant, but in this case it's a constant, so it's very easy to proceed. And then for Q3, it's minus 3 times Q1, so it's gonna be 15 nanocoulomb. And V3 is again just KQ3 divided by R, like this. Okay, so the total potential, you just add them up. And you can see that this number 45 degree here is actually not really relevant for this problem. I think it's there just to confuse you, to maybe think about the electric field instead. Right? So we don't use that here. So the answer V total is it's all K over R. So we can just do Q1 plus Q2 plus Q3. So that's going to be K over R times Q1, which is 5 nanocoulombs, plus Q2, which is minus 10 nanocoulomb, and then plus Q3, which is 15 nanocoulomb. So altogether it's K over R times 10 nanocoulomb. Okay, and then you just put R equal to 10 centimeters. So if during the exam you need to calculate the number, don't forget that you need to put everything in SI unit. So the last step, K is 9 times 10 to the 9. 10 times 10 to the minus 9, okay, that's nanocoulombs. And then divide by R, which is 0.1 meter, right? 10 centimeter is 0.1 meters. So you just do a calculator kind of thing, and then you can get the number here. Okay. Any question here? So one thing I want to point out is, what's the relevance of this information, this piece of information? It's a non-conducting arc of radius, whatever. So what if this is a conducting kind of material? Well, if that happened, then charge gonna move around like crazy. So we don't really, well, it's not like we don't want that, it's just change the question, right? The thing is that if everything is conducting, right, maybe it's made from copper or something, charge can move around. So all the charge will combine together and then redistribute themselves. So the 5 nanocoulomb minus 10 and 5 here will combine into 10 nanocoulomb, and it will just redistribute itself around this. Okay, and I think the answer will still be the same, but the charge configuration will be different. So that's kind of, maybe it's not so important in this case, but again, this problem is a little bit designed to maybe a little bit trying to confuse you by like different color here, but in the end you can see that it's not as difficult as it seems in the beginning. All right, let's do the next one. This one is RC circuit, so it might be a little bit difficult, but I'll let you do this for a few minutes. Okay, so let's talk about this. Um, you might remember from the lecture that when we have capacitor and resistor in the circuit, we need to solve differential equation. So that's actually not quite necessary if you want to know at two specific point in times. And those 2 point in time is exactly what's being asked here. So I'm gonna talk about the circuit later. But what is asked is at t equal to 0, what's the current? After a very long time, mathematically what this means is when t goes to infinity, what's the current in all resistors, right? So you don't need to, like set up the Kirchhoff rule and then try to solve differential equation or something like that. That's gonna be quite complicated and not necessary. Why? Because there are two facts that you can use for this kind of problem. First is that when C has no charge, and that's exactly what we have, right? Initially, the capacitor is completely uncharged. When C has no charge, it acts like a short circuit or just a piece of wire, okay, right at that moment. But then, well, okay, that's true right at t equal to 0. But when t increase a little bit, there's some charge building up in C. This is no longer true, okay? But that's not what we care, right? Because we care about when t goes to infinity. Sorry, when t equal to 0, what's the current? And the other thing is that when t goes to infinity, and we can probably say that when t goes to infinity, then the capacitor is fully charged. When C is charged, it acts like an open circuit. So let me demonstrate what I mean here. So let's look at A, which is t equal to 0. When you close the switch, right, the complete circuit looks like this. So when you close the switch, it looks like this. That's the circuit. When C has no charge, it acts like a short circuit. So that means you can forget about C here, right at t equal to 0. You can just replace C with, a piece of wire. So at t equal to 0, the circuit looks like this. So there's a battery here, R1, and then R2, and then R3. This is when t equal to 0. Okay? But when t is not equal to 0, maybe like 0.1 nanosecond or some other time, then there's some charge in the capacitor. This is no longer true. But at t equal to 0, this is the circuit. It's all 200 kilo ohm, right? Because that's 0.2 mega ohm. So it's all 200 kilo ohm, 200 kilo ohms. And then the battery is 100 volt, right? So what we want to find the current in all resistors, right? So we need to figure out the total resistance first. So these two are in parallel to each other, right? So when they are in parallel, then the resistance is reduced. So it's 200K here. Then this one is 100K. And then combine these two in series. Then you have the total capacitance, not capacitance, resistance to be 300K. Okay, so the total current in the circuit is I equal to 100 volt divided by 300K. So that's about, actually let me just make sure. I have the number correct. So 100 divided by 300,000. So that's gonna be 0.33 milliamps. So the current going through the first resistor here, I, is 0.33 milliamps. And then because these two resistors has the same value, the current is split equally. So that's gonna be 0.167 milliamps. And this is also 0.167 milliamps, something like this. Okay, so that's the current in the circuit at time equal to 0. Okay, again we ignore the capacitor because when there's no charge in the capacitor, then it acts like a short circuit. Now, what happens when t goes to infinity? Well, t goes to infinity, the capacitor is probably fully charged, and we can know that because there's gonna be some, well, the capacitor is supposed to be here, right? And there's some current going through the capacitor, so it will charge the capacitor slowly, and eventually it becomes full. When it's full, then this capacitor here will become open circuit. Open circuit is like when you disconnect the connection here. So the circuit becomes something like this. 200K. 200K. This is 200K. But it's open here due to the capacitor, which is full. When the capacitor is full, there's no current flowing through the capacitor. So that means there's no current flowing through this resistor either. Okay, so this I here becomes 0 milliamps because when the capacitor is charged, you cannot have any current. Sorry, I think I'm back again. So let me repeat what I say. So when the capacitor is fully charged, you cannot have any current going through the capacitor. Since the current cannot go through the capacitor here, the current will also not going through this resistor, right? So that particular resistor will have 0 current going through, right? So when t equal to 0, the current is 0.167 milliamps, but when times goes to infinity, right, after a long time, then the current becomes 0. So when the current becomes 0, all the current will flow through these two capacitors. So the circuit becomes something like this. Battery, and then one resistor, and then another resistor here. Right. So this will change because the other capacitor, it doesn't participate in the circuit. So that means the total resistance now becomes 400K. Okay, so the total current I here is the same total current that you have in this circuit. So I here will be 100 volt divided by 400K. So that's going to be 0.25 milliamps. And that's going to be this current, 0.25 milliamps, which is the same current flowing through this one and this one, right? Because the current cannot go that way because that's an open circuit. So all the current has to go through this resistor here. Okay, so that's the answer. So you can see that the current will be different when time equal to 0 and when time goes to infinity, right? Again, when you solve the differential equation and then you really prove that, you're gonna get the same answer. So you know a little bit more like what happened in between these two times, but in this case you don't need to do that. right? You can just use this kind of two facts for the capacitor to calculate this. Okay. So you don't need to use, 5 microfarad anywhere in this circuit. All right. So we can take a break at this point, but meanwhile, I will show you this problem. So if you have some time during the break, you can take a look at this first. But I'll be back in 10 minutes. Alright guys, let's continue. So in this problem, there's one equation that you, or one formula that you really need to remember, which is the definition of the capacitance. So if you remember, C is equal to Q divided by delta V, right? So remember what a capacitor is things that can hold charge when you apply some potential across the two terminals of the capacitor, right? So if you reverse this, then you can get delta V equal to Q over C like this. And the other thing that you need to know is how to combine capacitor together. So that's being asked for the first question. Find the equivalent capacitance of the system. So you have 4 capacitor connected like this. Capacitor and resistor use, the formula the other way around. So when capacitor are in series, I just write 3, but let's understand that 3 means 3 microfarad. So 3 is 6, 2, and 4, right? Um, we need to combine the one in series and one in series down here first. Series capacitor you combine using this formula 1 over C total equal to 1 over C1 plus 1 over C2. Okay, which is the other way around if you talk about the resistor. So don't get confused by this. So for the blue one, you have 1 over C total is 1 over 6, 1 over 3 plus 1 over 6. This is 3 over 6, which is 1/2. So C total is 2 for the blue side, and for the yellow side, one is again in series, so you need this formula 1 over 2 plus 1 over 4, so that's gonna be 3 over 4. So C total for the yellow one is 1.33 something like this. Okay, so that means the next step is to combine the two, which is like this. So this is 2, this is 1.33. When you connect capacitors in in parallel, you need to just add them up. So this one is easy, so it becomes 2 plus 2.33, so 3.33, like this. So this is the equivalent capacitor, equivalent capacitance of the system. So C equivalent is 3.33 microfarad. How did you get 2 and 1.33? Use this formula here. 1 over C total is 1 over C1 plus 1 over C2. And it's this one here and this one here. So it's 1 over 3 plus 1 over 6. Right. So how do you get this one? So 1 over 3 is 2 over 6, right? So 2 over 6 plus 1 over 6 is 3 over 6. So 1 over 2. So 1 over C total is 1 over 2. So that means C total is 2. Is this clear to you? The same for this line. 1 over C total. So yeah, so we just flip 1 over 2, and I think you mean 1 over 2. So you just flip 1 over 2 and 3 over 4, right? Because it's 1 over C is this number, so you just flip it. Yeah. Exactly. Okay, cool. So that's the that's A, right? And then for B, find the charge on each capacitor. Well, this one is easier if you work backward, because once you know the equivalence capacitance, you can calculate what's the total charge on each capacitor. But I think it's easier if we start here, because that's gonna be, I think, more convenient if we don't do the last step. So let's look at this equivalent circuit, which is combining the two capacitors. Well, not like the two sets of capacitors. So you have 2 and 1.3 microfarad here. And the voltage on the battery is 90 volt. So I want to find the charge on each capacitor. So if you have two capacitors which is connected in parallel like this, they have the same voltage difference. So these two have the same voltage difference, which is 90 volt. So I can calculate the charge, let's say plus Q1, plus Q2 here. So plus Q1 charge, go back here, is just voltage times capacitance. So it's gonna be 90 volt times capacitance, which is 2 microfarad. Okay, so the answer is gonna be 0.18, I think, millicoulomb. Actually, let me keep it as microcoulomb. So 180 microcoulomb for the first one. And then for the second one, this one is plus Q2 equal to the same voltage, okay, 90 times the capacitance, which is 1.33 microfarad in this case. Right, so if you calculate this, then you get 120 microcoulomb. So you can see that the top one has plus 180 microcoulomb. The bottom one has plus 120 microcoulomb. They are not the same because they have different capacitance. Okay, so the one with more capacitance gonna have more charge. So you can calculate it like this. So let me color code this so that you can know where this comes from. So 90 is the voltage of the battery. Okay. The reason why I do it at this stage, not the last one. The last one is not so useful because you just gonna get, the combined total charge, but you have to split it anyway. But once you know that this is 180 microcoulombs, for the capacitor which is connected in series, the charge gonna be the same on each capacitor. So that means we are done actually for this part. Because this is 180 microcoulomb, it's gonna also be 180 microcoulomb on the other capacitor. So capacitor connected in series, they will have the same charge. So the bottom one, which is 120 microcoulomb, is gonna be also 120 microcoulomb on each one on the bottom here. Okay, so 180, 180, 120, 120. So that's the answer for B, which is the charge on each capacitor. And the last question was the potential difference on each capacitor. Well, the potential difference on each capacitor, you just calculate V equal to Q over C for each capacitor. Okay, so for example, this one here, the charge is 180 microcoulomb. The capacitance is 3 microfarad. Actually, let me call this one 1, this is 2, this is 3, this is 4, so that I can write it here. So V1 is just Q1 divided by C1. So Q1 is 180 microcoulomb. C1 is 3 microfarad. So if you calculate this, then you get 60 volt. And V2 is Q2 divided by C2. That's going to be 180 microcoulomb, right? So it's the same charge divided by different capacitance. So that's going to be 30 volt. So you can see that V1 is 60, V2 is 30. V1 plus V2 is 90, which is the potential of the battery, which is what it should be. And then you can go on with V3. So V3 is different amount of charge, so that's going to be 120 divided by 2. So that's going to be 60 volt. And then V4 is going to be 30 volt. So you can do that yourself. Okay. Again, V3 plus V4 has to be 90 volt, which is the total voltage of the battery. Okay, so you can see that everything is kind of self-consistent. It's not too difficult, but it's also not too trivial. So make sure that you understand what I'm doing in every step. Otherwise, it's gonna be quite confusing. Okay, but again, let me remind you the important point. Okay, of course, you need to know this formula because that's the definition of the capacitor. And you have capacitor in series, you need to add them like this. This is also here, right? And once you have them in parallel, then you can just add them up. So it's 2 plus 1.33 becomes 3.33, right? And then the other thing is that when capacitor are connected in series, in parallel like this, they have the same voltage across them, okay? For capacitor which is connected in series, they have the same charge on each one. Okay, so from all that information that you can calculate exactly what I did here. You want to view the previous page, this one. Is this the one you want, or which page do you want? Okay, this one, right? Okay, so let's move on to this one again. This one is Kirchhoff rule, so it might be a bit difficult. So I'll give you a few minutes. Okay, so this one might be a little bit more involved in terms of calculation, so I will just start talking about this. This is a kind of like classic problem for Kirchhoff rule. So remember there are two rules. One is the current rule. What is the current rule? Well, the current rule says that if you have any junction, the current flowing in must be equal to flowing out. Okay, so if I say the current in this branch, this one, okay, and it's flowing, let's say this way. So when you do this, don't worry too much about, okay, what exactly the direction of the current, because if you get the current direction wrong, you get a minus sign in your answer, so you just flip it in the end. So there's nothing bad about that. So let's call this I1, okay, and I will call this I2. When this is the case, this current here, you can call it I3, but then you have three variables, I1, I2, and I3. But I1 must be equal to I2 plus I3, right? So I can just say this is I1 minus I2 instead of calling it I3. So here I'm using the current rule, right? Because I say that the current flowing in this case is just I1, must be equal to all the current flowing out, which is I2 plus this one. So this plus this is I1, which is equal to I1 flowing in, right? So I don't need to write down I3 because that's going to be three variables. I can reduce it to two variables, I1 and I2, like this. Okay, so once we are done with labeling the current, next is to figure out the loop rule. And we probably need two loops because there are two variables. So two variables, you need two equations, and each loop you probably get one equation. So I'm gonna start here at point B, and the first loop is gonna be this loop. The small one. So I'm gonna walk along the loop and noting that the current might be different in each section. Okay, so this one is I1. Another thing you might need to know is this is also have to be I1. Okay, because from here to here there's no branching, the current has to be the same. So for loop number one, which is the pink one, loop number one, you go around this, there's no resistor, so nothing to write down, and then you turn right here, you're going against the battery. Usually you go along with the battery, so you just add the voltage of the battery, but in this case you're going against the battery, so it's going to be minus 60 volt for this battery. And then you go along with the same direction as I2, and then you go across R2, right? When you go across R2 in the same direction as the current, you need to put a minus sign. So it's going to be minus I2 times R2, which is 3000 ohms. And then another right turn here, again going along with the current. Sorry, this should be I1. This is I1. Okay, so going along with the with the current I1 across resistor R1, so I need minus I1 R1, and then I walk across the battery. Now I walk across it in the direction that we usually see, right, which is from negative to positive, so you want to put plus 70 here, and then you're back to the original point, which is point B, so you can complete the equation by setting it equal to 0. So that's the first equation. Okay, you can put the resistance in the equation, I think, now. So let me simplify a little bit. So minus 60 and 70 give you 10, obviously. So So you get I2 times R2, which is 3000. And then I gonna flip it so that it becomes become plus. This equal to 10. Okay, so this equation is just the same equation that I have here, but I put in the number and then I rearrange a little bit. Okay, so hopefully don't get confused by this. Let's do loop number 2. Loop number 2, we're gonna start at the same position, but then we're gonna go around the big loop here. Okay, so it's the green one that we are gonna go. So part of the loop will be overlapping the first loop, which is fine. There's nothing wrong with that. I mean, you don't need to force yourself to go to a different loop like this. So let's write down loop number 2. Loop number 2, starting from here, again, I1 is not going across any resistor, so it's fine. So the first resistor we go through is R3. So it's gonna be minus the current, which is I1 minus I2 times R3. And then going against that battery, which is 80, so minus 80. And then back here, it's gonna be the same as what we had before, which is minus I1 times R1, and then plus 70, which is the last battery, this one. So again, the last one is plus 70 because we are going from minus to plus of the battery terminal. We are not going against the battery. And then we complete the loop, so we just put it equal to 0 here. And then let me simplify again. So I have minus I1 times R3, which is 4000. And then minus minus become plus, so I have plus I2 4000. And then 80 and 70 I get minus 10. And then minus I1 times R1, which is 2000, equal to 0. So this I1 can be combined together. So I get minus 6000 I1 plus 4000 I2 equal to 10. Right, so I move this to the other point. And the only thing left to do is to solve this equation. Right, so you have this equation, I2 times 3000 plus I1 times 2000 equal to 10. And then you have another one here. So your task here is just to solve for I1 and I2, which I'm not gonna do that because it's just mathematics. So you can do that later. But the next thing we need to find is find the potential difference between point C and F. So where is point C and F? C is here and F is here. So what's the potential difference? For the potential difference, you need to know I2. For let's say you don't have R2 here. Let's say you don't have R2 here. Then the potential difference will be just coming from the battery 60 volt. So the answer will be 60 if you don't have R2. But since you have R2, you need to subtract the potential difference across R2. Right, so I'll just write down the answer. Because we need I2, I haven't found that. You need to calculate I2. So once you know I2, then the answer for B will be 60 minus I2 times R2. Okay, that's the potential difference across C and F. You can also use this one to calculate. It's gonna be 80 minus IR of that guy. For this one, it's gonna be 70 minus IR of that guy. So you have 3 choices to calculate. It's you're gonna get the same answer here. Okay, let's move on to the next question. The next question is about magnetic field. So again, I'll give you maybe a few minutes to look at this one. Okay, so let's look at this. So in this case, we have negative charge, which is an electron, right? Going inside this region with magnetic field. So in this region, there's no magnetic field, but here there's some magnetic field. So electron will feel some kind of magnetic force on the electron. So the first is determine the time interval required for electron to leave the field region. So we need to think about what happened to the electrons when it's going into this region. Well, remember the magnetic force Fb equal to QV cross B, right? And inside this region with magnetic field, electron is going to the right. The magnetic field is into the page. So you need to use your right hand rule to figure out which direction is the force. And remember that electron has negative charge, so you need to flip the direction of the force after you have done the right hand rule. Okay, so again, please convince yourself that the force on the electron is going down. And we also know from our lecture that the charge particle in magnetic field, like what we have here, gonna travel in a circle, right? So if all the region is filled with magnetic field, it's gonna go around in a circle like this. But since it's only half of the region, so what's gonna happen is that it's gonna travel in a section of the circle in the region with magnetic field, but after it leaves the region with magnetic field, it will just continue on with a straight line. So the trajectory of the electron will look like this. It's gonna go in like a straight line, entering the region with magnetic field, gonna curve around in a semicircle here, half a circle, and then come out like this. So the question here is determine the time it takes for the electron to travel in the field region, noting that the electron path is semicircle. So essentially, how long does it take? How long does the electron spend time for this half of the circle? And if you remember, the cyclotron motion is actually half the period, right? Because the whole period is to cover the whole circle. This is half of the circle, so it's just half of the period. Okay, so if you don't remember, well, you can always start with F equal to QVB equal to mv squared over r, right? So the radius is v equal to mv divided by qv. Okay, so how long does it take? Well, this is half of the circle, so it's half of the circumference. So the distance is not 2 pi r, but it's just pi r, right? Because it's just half of the circumference. So the distance is pi mv divided by qb. So the time it takes is just distance divided by how fast it's moving. So it's just pi m divided by qb. Okay, so this is the time it takes to complete the half circle radius, half circle distance. So pi, you know, mass you also know because the mass of the electron. Q is the electron charge, right? So it's E, so it's 1.6 times 10 to the minus 19. And what is B? Well, B is given here is 1 millitesla, so 10 times minus 3 Tesla. So you can calculate this. Okay, so I got, I'll just write down, but you can do the number cranking yourself. Like this. Okay, so this is the answer for question A. And then for B, assuming that the maximum depth of the penetration into the field is 2 centimeters, find the kinetic energy of the electron. So you can see that the time here, since we cancel out, the velocity cancel out, you don't need to know how fast electron is moving to get the answer for A, right? So that's why B gives you additional information. So what is B telling you is it's going into the region with 2 centimeters. And what is that? That's actually this distance here. So it's telling you that this distance is 2 centimeters. And that's just the radius of the circle, right? So in other words, for part B is telling you that R is equal to centimeters or 0.02 meters. So you can use part B to find the velocity, and then you can find the kinetic energy of the electron. Okay, so since we are running a bit out of time, so I'll just write down briefly what you need to do. So use R equal to mv over qb, solve for v, and then the kinetic energy is just 1/2 mv squared, and use v that you solved earlier in this equation. Okay, so that's what you need to do to answer part B. Alright, so it's not too complicated, I hope. So I only have 10 minutes, so next one I'll just start talking. We have one more question here. Actually, two more. So what is this? This one is a long straight wire on horizontal table, and it carries a current of 1.2 microamp. So it's a wire, and it has the current 1.2 microamps. And we have a proton which is above the wire, and it's going in the opposite direction. So in the side view, you're gonna have the wire going this way, and the proton is above the wire, and this is distance d. We also know how fast the proton is moving. Okay, ignore the magnetic field due to the Earth. Determine the value of d. So what's going on here? Well, the thing is that the proton has some mass. If there's no current here, the proton will just fall down due to gravity. But since there's a current here, there will be a magnetic field going in the direction due to the wire. And again, you need to convince yourself that this is the direction of the magnetic field. So this is B field from the wire. It's going to the right. The proton is going in out from the page. That's the velocity of the proton. Okay, so because V of the proton is going out from the page, B is going to the right. The magnetic force actually point up. So FB point up. And that makes sense because the whole purpose of this problem is for the magnetic field to balance mg, which is coming down. So that's what's going on here. All right. And what's the distance here has to do with the thing? Well, the distance gives you the strength of the magnetic field. Right. So if you remember, if you have a wire and a distance r from the wire, right, what is the magnetic field? The magnetic field is given by mu0 I divided by 2 pi r. Okay, so the closer you are to the wire, the stronger the magnetic field. So this one, you just need to find d such that the magnetic force balance the weight of the proton. Okay, so what you do is you just say FB equal to FG. FG is the weight. I can just say W maybe, like this. So FB is QVB equal to mg, right? That's the weight. And what is b? Well, b depends on the distance, like this. And in this case, we used to use d. So it's qv times mu0 I divided by 2 pi times d equal to mg. And then you just solve for d in this equation. Let's check if we know everything. We know v is given here. We know I is given here. We know g, that's 9.8. The mass of the proton we know. The charge of the proton we also know. And mu0 is the constant, right? It's called the permeability. So you can look that up in the lecture, but it's a known number. So in principle, you know everything. So you just need to solve for d in this case. All right. So it's actually not too complicated for this one. Again, I'll ask you to complete this one by just putting in to the calculator. Okay, any question here? All right, let's talk about the last one here. This last one is something that you need to look up in the lecture. So what we need here is we need to find the magnetic field at point P, right? And the one thing that we need from the lecture is the magnetic field at the center of the loop, right? Remember, this is where you need to use the Biot-Savart law, but you actually can just use the result from the lecture to calculate. If you don't remember, I will just quickly remind you how to calculate. Again, you don't really need to know this, but so it's dB equal to mu 0 divided by 4 pi, I think. And then IDL cross R divided by R square, right? So remember this is the Biot-Savart law. But again, the cross product gives you the direction of the magnetic field. And since the magnetic field at the center is the same direction from every section of the circle, so we can simply just ignore the direction, right? Because we know that it's going to point into the page if the current is going this way, and it's going to be out from the page if the current is going the other way, right? But the total magnetic field is just integrating this 1 over R square, calculate integrate of this, and this one is the whole length of the circumference, so it's going to be 2 pi r. So the magnetic field at the center is mu 0 I divided by 2r. Okay, so 2 pi cancel with 4 pi, and then you're left with this. But again, you don't need to recalculate this. You can just use this from the lecture. So how do we apply this into this kind of question? Well, the section that you have here is not going to contribute to this part, to the magnetic field at point P, because the cross product here will be 0. And also, if you remember Ampere's law, right, this point P is actually kind of like 0 distance from the current I, so it's actually not going to contribute. So the only thing that contribute in this diagram is this arc here. That's why the magnetic field is non-zero. So let's talk about the direction first. So since the current is going that way, using your right hand rule, the magnetic field at point P is going into the page. Okay, and we know that if you have a complete loop, the magnetic field is given by this. But if you have only partial section of the circle, then it's gonna be less, right? So the only thing that you need to do here is to replace I with just the I from this section, right? So if this I is the I for the whole loop, then the I on this loop, on this section, will be just the arc length, S here. S is R times the angle here, right? So it's just the ratio of the arc length to the whole circumference of the circle. So for the magnetic field at point P here, B is mu 0 I divided by 2R, and then you need to multiply by the factor of R theta divided by 2 pi R, right? Again, this one is coming from the arc length divided by the length of the circumference. Okay, so you have mu 0 I divided by 2R, and then theta divided by 2 pi, like this. So that's going to be the answer for the left one. So the right one, again, this section of the wire will not contribute to the magnetic field. So the only thing you need to calculate is from this and from that. So the inner semicircle and the outer semicircle. Okay. It's half of the circle, so it's actually very easy to just divide by half. But the distance is different. Okay. So one will be stronger than the other one. So this one will be stronger because it's closer. So the magnetic field, the net magnetic field, will be going into the page for this case. be filled into the page. And the answer will be mu0 I. So they all share the same current, so I can take it out. Divide by 4. Divide by 4, not by 2, because it's half of the circle. Okay, and then it's gonna be 1 over 1.0 centimeters minus 1 over 2.0 centimeters, like this. It's minus sign because for the inner circle it's going this way for the current, and for the other one it's going the other way. So the magnetic field point in the opposite direction. So you need to subtract them, right? Because magnetic field is also a vector. Okay, so just running out of time here. So that's it for today, and that's it for the lecture that we have. Let me remind you again that the final exam is about 10 days from today, 11 days, so it's on the 26th. Any more information I will announce to the Canvas system, okay? I have to talk to Ajahn Vitun because we have 2 sections, so I don't have anything, specific right now. But I already post we don't have class this next week. This is the last week of the class. Next week you have finals, right? So you can look at the sample final exam that I already posted a long time ago on the Canvas system to get a feel on what to expect, all right? But I mean, other than that, thanks for this semester. Even though I have no chance to see any of you in person. So, well, it's been strange using all like online lecture. But anyway, thanks for keeping up with all of this, and good luck with the final. If you have any question, you can just email me, about the material, about the homework, or anything. All right. You still have one homework which is due on Sunday, I think, and I will post the solution after the due date. Okay. So good luck, everyone. Not just for this class, in any class that you are taking. So I will see you on the final exam day, which is the 26th then. Okay? So thank you everyone so much for this semester. I really appreciate it. And good luck. Take care and see you later.